Hi everyone. In this lecture, I'll discuss about deriving transfer functions for first order RL circuits. I wanted to discuss about time domain response for first order RL circuits, but I thought first once we derive transfer functions, then it'll be pretty intuitive to draw the time domain responses for first order RL circuits for various inputs. So first I'll start with the series RL network. So if you understood a series and parallel RL network, it's pretty simple to analyze. It's pretty simple to analyze any first order RL network. Okay, so if you are asked to plot the impedance of this network as a function of frequency, the magnitude of the impedance as a function of frequency. Now when you have two elements in series, I'm going to draw the impedance of resistor as a function of frequency. The impedance here is R plus SL, or if I substitute S equal to j omega, I'm going to get R plus j omega L. Now I'll plot the impedance of the resistance. R is going to be constant as a function of frequency. Now this term omega L is going to increase linearly as a function of frequency. Now the overall magnitude is going to be a complex addition, so it's going to be root of R square plus omega L the whole square. Okay. So for after the frequency R by L, okay, this function, if I'm going to plot this magnitude, it's going to increase linearly. So what this graph shows is that for lower frequencies, a series RL network behaves like a resistor. So always remember, when you add two elements in series, the impedance of the larger element, okay, the larger the impedance of the element, that's going to determine the overall impedance of the network. So if I have two elements in series, the element with the larger impedance will dominate the overall impedance. So at first, for low frequencies, an inductance behaves like a short circuit. So the impedance here that is shown here, it's slowly increasing as you increase the frequency. So resistance is larger, so it will dominate for low frequencies. When I say low frequencies, frequency is less than R by L. After that, so that is the frequency when omega becomes equal to R by L. So what happens to your impedance is that your impedance becomes R plus j omega L is the impedance. The complex part of the impedance becomes JR. When omega equals R by L, it becomes the complex part of the impedance also becomes equal to the real part of it. After this, the omega L is going to keep on increasing linearly with frequency, and eventually it will dominate. It will eventually start dominating the overall impedance. So for low frequencies, the series RL network behaves like a resistor, and for high frequencies, it behaves like a inductor. So I can ignore the R term, and this becomes simply j omega L. So here it will behave like an SL, and here in this region it behaves like a resistor. So the effective graph is going to look something like this. The impedance plotted as a function of frequency. Now similarly, when you try to plot the impedance of a parallel RL network, so inductor and resistor in parallel, so intuitively we can see at low frequencies, when you have two elements in parallel, the element with the lower impedance will dominate the overall impedance. So inductor impedance is going to be very low at low frequencies. So the inductor impedance is going to be linearly increasing like this, and the impedance of the resistor is always constant. Okay, so whenever, as I said, if two elements are in parallel, the lower frequency, the element with the lower impedance will dominate the overall impedance. So initially the inductor impedance will be dominant. After that, the circuit will behave like a resistor. So for low frequencies, when I say low frequencies, for omega less than R by L, this network is simply going to behave like an inductor. And as you increase the frequency, as you increase for omega greater than R by L, much greater than R by L, the impedance will simply reduce to R, because inductor is going to have much higher impedance, so we can ignore the inductive impedance part. Again, you can show that at omega equal to R by L, the impedance of the inductance and the resistance will be same. Okay, the overall impedance is going to be R by root 2. So the characteristic would look something like this. So I'll draw the overall characteristic. So initially it will behave like an inductor, and at higher frequencies it's going to behave like a resistor, and at omega equal to R by L, the value of this is going to, magnitude is going to be R by root 2. And similarly, I can show that I didn't show it here explicitly for a series resistance, but the value at omega equal to omega equal to R by L, the value of the resistance is going to be R into root 2. Okay, so because it's getting added here, the resistive impedance, on the other hand here both of them are in parallel, so the effective resistance will be lower than R, so that's why you are getting R by root 2. Okay, so for a parallel RL network, for low frequencies it will behave like an inductor, for high frequencies it will behave like a resistor, and the opposite is true for a series RL network. So I'll now start analyzing, we'll start deriving transfer functions and draw the frequency response for different first order RL networks. So we already discussed how to derive transfer functions for first order RC circuits. All you need to do is find out the DC gain, and this is valid for transfer functions which has a finite 0 and a pole. So you just need to find the pole and 0 and the DC gain. If you know all the three quantities, then you know the frequency response completely. So for this circuit, output is taken out as a resistor, input is applied at this point. To find the DC gain, as I said, now there is a series RL network, so you can ignore the inductor. For low frequencies it will behave like a resistor. So the circuit is simply going to reduce to this. The gain of the circuit is half, so H of 0 is half. Okay, the next thing is I'm going to find the poles and zeros. So first, as I discussed in the previous lectures, if you can, I think it's one of the previous lectures, I think lectures 19 to 20. You can just go through the previous lectures. How did we find the poles and zeros if I have an impedance network of this type? For you to find a 0, there are two possibilities. Z2 should be equal to 0, provided Z1 is not equal to 0. And the second case is Z1 tending to infinity, provided Z2 is not infinity at that point. Okay, Z2 should be finite. So if using these two conditions, we could actually find poles and zeros for any simple first order RL network. So using that, I am going to first start with a simple, the circuit which we had already analyzed. Now if you look at this, for you to get a 0, this impedance should go to 0, but that's a resistor, so it will never go to 0. So that condition is ruled out. The other possibility is when this impedance blowing up to infinity, and that will happen only at omega equal to infinity, because that will happen when when omega L becomes infinity. That will happen at infinite frequencies. Inductor will have a very high impedance, so that tells us the 0 is at infinite frequencies and at an infinite frequency. Now the only other way, which means there is no 0 on the circuit at any finite frequency. Now the only other thing to find out is the pole. Now to find the pole, as I said, you can simply short circuit this node and equate this impedance. Z1 equals minus Z2, that will give you the pole. Okay, if you do this, you will get that. So that will be SL plus R equals minus R. So SP, the pole, will be minus 2R upon L. Or you can simply find the effective resistance seen by the single inductor, because mostly in most first order circuits you can have a complex network of resistors and just one inductor, or you can have many inductors and just one resistor. So in both the cases, you can, if you have one inductor and many resistors, you just have to find the equivalent resistance seen by the inductor. Okay, and in the other case, when you have many inductors and just one resistor, in that case you just have to find the equivalent inductance seen by the resistance. So that will give you the total. Then the time constant will be simply L equivalent by R, or R equivalent by L, or L by R equivalent, depending upon the circuit. You can find the time constant. Once you know the time constant, 1 by time constant will be equal to your pole. Omega p will be 1 by tau, and if it's a left of plane pole, it will be SP is minus omega p. So this is what we discussed in the previous lectures on RC circuit. The same thing can be applied here as well. Okay, so you can very easily see the effective resistance seen by the inductor is minus 2R. So the pole is minus 2R by L, or the time constant is L by 2R. Okay, so from that we can get this. So now in this circuit, the DC gain is half. There is no 0 in the circuit, and there is a pole at 1 plus, there is a pole at 2R by L, or 1 plus S tau SL by 2R. So that's the transfer function for this circuit. We can very easily see that what happens in this circuit is you have R, L and R. At low frequencies the gain of the circuit is half because inductor is a short circuit. Okay. At very high frequencies what happens is that at very high frequencies the inductor behaves like an open circuit and the entire voltage will drop across this. Vi or the when I apply a step input it's entirely going to drop across this. Okay. Or the entire input voltage is going to drop across the inductor because the inductor impedance becomes infinity. And the voltage across the resistor is going to be 0. And that's nothing but a low pass filter. Right? It completely rejects the higher frequencies. So if you plot the frequency response, you start with half and then you should normally plot it on the logarithmic axis. So this half will be minus 3 decibels. When you take 20 log of half, it's minus 3 dB. And then it will roll off at the slope of minus 20 decibels per decade. Okay. Now in the other circuit, you are given R, L in parallel and then instead of them being in series, this is the circuit. Now you are quickly, you are supposed to derive the transfer function for this circuit. So in this circuit, again, if you can see there is only one inductor, so we know it's obviously a first order system. Now the DC gain, to find the DC gain, you have to just short circuit the inductance. So once the inductance is short circuited, your V0 equals Vi. So which means your DC gain is 1 in this case. The circuit simply reduces to this. So again the parallel resistor doesn't matter because once the inductor is short, the entire current will flow through the inductor. Okay. Again, when two elements are in parallel, the lower impedance always dominates. So the inductance impedance being 0, that's going to completely dominate whatever you connected in parallel with it. So the circuit is simply going to reduce to this. The H of 0 is 1. Now the next thing is we'll find the zeros in the circuit, zeros and poles. So first to find the 0, we can first either equate this to 0, and that's never possible because it's a pure resistor. It's not a frequency dependent element, or it doesn't depend upon S. The other possibility is when this blows up to infinity. At that point Z2 is finite because it's just a resistor, and this will blow up to infinity when we discussed when I have two impedances, say Z and minus Z in parallel, I'm going to get an effective impedance of infinity. So that will happen when SL equals minus R, or S, the pole frequency, the zero frequency in this case, SZ, it's a left of plane 0, it's going to be minus R by L. So I'm going to write omega Z as R by L. Okay. Next you have to find the pole. To find the pole, as I said, always short circuit the input and then find the net resistance seen by the inductance. So then from that you can compute pole as, first we can write the time constant. That will be L by R equivalent. In this case it will be R by 2. So it will be 2L by R, and the pole will be R by 2L. So in this network you can see the DC gain is 1. If I start, H of 0 is 1. So the transfer function will be 1 into 1 plus S by omega Z, so which will be SL by R by 1 plus S2L by R. Okay. So now first we will encounter, if you look at this expression, the 0 is actually R by L and pole is R by 2L. So first you will encounter the pole, which is 1/2 of R by L, and then at omega equal to R by L we are going to get the 0, and at that point for high frequencies the gain has to be half. H of 0 is 1 here, it's going to be half. We can very easily see in this circuit, let me just redraw that. So at high frequencies inductor will behave like an open circuit, so I can just open it out and you can very easily see the voltage gain for this circuit is going to be half. Okay, this is Vi, you are going to get half of Vi across the resistor. So therefore it has to be half. And as I said, we don't need to find the high frequency, it will automatically be you can get that high frequency gain once you write the transfer function. So transfer function, you just need to know low frequency gain, poles and zeros, then the high frequency gain is uniquely determined by them. Also, I'm not drawing the phase response. We have already drawn phase responses for first order systems extensively. So if I have pole first and the 0 next, it's going to be a lagging phase system. You can easily draw that and show it. I'm not drawing it, I'm just going to show it for one example. And then eventually the phase goes to 0 at high frequencies. Okay, the signal and the input and the output will be in same phase. And we also showed where does this occur. It occurs at the geometric mean, the peak of the phase. Okay, I'm sorry, this is a lagging phase, so I have to show it in the negative axis. If the pole comes first, then it's a lagging phase system. So you're going to have a lagging phase relationship. Okay, and the peak value of the phase is going to occur at a frequency which is root of omega p omega z. We showed this in one of the previous lectures. You can refer to that. Okay, so that's how you draw the magnitude and phase response given any first order RL circuit. Now I'll start analyzing circuits with more than one inductor, which happen to be first order systems. Now if you look at this circuit, there are actually two inductors. So when I have two inductors, then I can at max the system order can be 2, because let's assume the voltage across inductor 1 as V1 and the voltage across the other inductor as V2. Then I'm going to get an equation of this form, some A0 dV1 by dt plus I might if I write a KCL and KVLs in this circuit, I can actually get an equation of this form, A0 dV1 by dt plus A1 dV2 by dt, okay, plus V1 some B0 V1 plus B1 V2 equals 0, or some constant or input equal to Vi. I am going to get one equation. So here there are two unknowns. So then we might, since there are two unknowns, and we can actually have two differential equations in terms of V1 and V2. Okay. Also, we can actually show there are two unknowns in this equation. Okay. Now to find the solution for this equation, we need one more equation, because one equation is not sufficient. There are two unknowns in this equation. If you look at this circuit, the current in both the inductors are same. So because of that, I can say L di by dt must be equal to L di by dt. So V1 equals V2. Okay. Or let's say I have an equation in terms of V1 and V2, and I have another equation which relates V1 and V2 linearly. V1 plus V2 equals to some constant k. Then I can substitute either for V1 or V2 in this equation and reduce the first equation to a simple first order differential equation either in V1 or in V2. Okay. So therefore, from that argument I can say that if you have a linear relationship between the two variables and you have one more equation containing a differential terms of both the variables V1 and V2, that can still be a first order differential equation. That can be reduced to a simple first order differential equation. So that's what I had already discussed, the same point for capacitors. Okay. So if I substitute V1 in this equation in terms of V2 or V2 in terms of V1, I can simply reduce the first equation to a simple differential equation either in terms of V1 some constant k, some coefficient or some constant alpha. Okay, I can reduce it in this form, or I can reduce it to an equation of this form, some beta V2 equals Vi. Then once I know V1, I can use this equation to find V2. They both are linearly related. Okay, so that's how, even though there are two energy storing elements, even though there are two inductors, their voltages or currents can be linearly related to each other. There is a relation which relates both either the currents or the voltages through a linear equation, and once we have that, then the order is going to be one, or in this case it's going to be a first order system. Okay, so I'll quickly start writing the transfer functions. Okay, now in this circuit again we know that it's a first order circuit because, as I said, there is a linear relationship between the voltages of both the inductors. Okay, now from this I can actually write the transfer function. So first we'll write the DC. We need to find the DC gain. For DC, inductors will behave like a short circuit. So I can ignore the inductors and the circuit simply reduces to this, and the gain for this circuit is 2 by 3 DC gain. This is your H of 0. So next we are supposed to find the poles and zeros. So if you are supposed to find the poles and zeros, now first we'll find the zeros. The 0 can happen when this impedance becomes 0. This impedance tends to 0 at a finite frequency. That happens when SL equals minus 2R or SZ equals minus 2R upon L. So this is the frequency at which you get a 0 in this circuit. You should remember that at this frequency, this impedance is non-zero. Okay. And similarly, can this impedance blow up to infinity? We are trying to find the other possibility of a 0. That impedance can blow up to infinity only when omega equals infinity. So again I can discard that. So there is only one 0 in the circuit. Now to find the pole, since we know it's a first order circuit, I can short circuit this input and then find the effective total inductance and find the resistance seen by the total inductance, or the mathematical definition what we discussed in one of the previous lectures is just equate the two impedances with negative signs. So SL plus R must be equal to minus of SL plus 2R. So from this we can very easily show that the pole is going to be minus 3R upon 2L. Okay. So as I said, that effective resistance here is, inductance here is 2L, and the resistance seen by the effective inductance 2L is simply 3R. So it's going to be, pole is going to be 3R by 2L, or time constant in this case is going to be 2L by 3R. So from this I can very easily write the transfer function, which is going to be H of 0 is 1, and then the 0 is going to be 1 plus SL by 2R. Okay. So from this I get the 0, and the pole is going to be 1 plus one plus S into 2L by 3R. Okay. The DC gain is 1. DC gain is here is 2 by 3. So when you are going to plot this transfer function, you will start from 2 by 3. The pole here is at 3R by 2L and 0 is at 2R by L. So this is nothing but 1.5 R by L, and this is 2R by L. So first you get the pole, and once you hit the pole, after that you are going to hit the 0. That's going to occur at 2R by L, and this is 1.5 R by L. So from 2 by 3, the gain is going to reduce to half. Again, you can very easily show that. You can easily derive the high frequency gain from the circuit itself. So just assume inductors are open circuit, or inductor impedance is much higher. You can ignore the resistive impedances. The circuit will simply reduce to, at high frequencies, I can ignore the series resistors. The circuit will reduce to this. So the gain is going to be half. Okay. Okay. So with this, we actually discussed how to find the transfer functions. I'll just take a few more examples to derive transfer functions. Now we'll do it very quickly using intuitions. So the DC gain for this circuit is going to be 1. This inductance will be short circuit. Okay, the output voltage is taken here. You are applying the input voltage at this point. So the DC gain for this circuit is going to be 1, and the 0 is going to occur when this impedance goes to 0. Okay, and that will happen at, yes, you can very easily see that it's SL equals minus R, so S0 equals minus R by L. Okay, and then the pole, again there are two inductors in the circuit, so you can find the equivalent inductance seen by the resistor, which is going to be 2L. So the pole is going to be R by 2L. Okay, so if I write the transfer function, it's going to be 1 plus the 0 S by omega Z. So omega Z is R by L, so SL by R, and then the pole, so here the time constant is 2L by R. Okay, it's 1 plus S tau, so 1 plus S into 2L upon R. Again, we can very easily see at high frequencies the circuit will simply reduce to 2 inductors and the gain is half, and you can show that in this transfer function when you draw it at high frequencies I can ignore the 1 in the transfer functions, so it will be SL by R by S2L by R, and this will tend to half. So that's how you get that. Okay, and you can easily draw the Bode plot. We have already discussed that for this. Okay, so here in this circuit I think the 0 occurs at R by L, the pole occurs at R by 2L. You get the pole occurs at R by 2L. Okay, yeah, so you can actually draw the transfer function once you know the poles and 0 locations. That's it. Now I'll discuss the another circuit which we already discussed, a very interesting circuit based on this for capacitive. So now in this circuit, if you are if you are asked to derive the transfer function for this, again we will go by the same rule. First you have to find the DC gain. So again, whenever you are drawing transfer function, so first thing is if you know that first, if you know the DC gain is going to be just 2 inductors because they are the low frequency impedances are lower in frequency. The low frequency impedance is very low for inductance, so I can actually ignore the resistors. Okay, so the circuit is going to reduce to this. The low frequency gain is half. At high frequencies I can ignore the inductors because inductive impedance is going to be very high. The circuit is going to reduce to this. The high frequency gain is 2 by 3. So now on a frequency graph, on a frequency response graph, if you draw the half, the DC gain, and then the high frequency gain, it is actually greater than the DC gain. Now to reach from here, that is a DC gain, to this high frequency gain, you have to first encounter 0. You can't, it won't happen if you encounter pole first. You have to first encounter 0 and then the gain has to rise, and then you have to encounter pole. So from that we can say you are going to have 1 0 1 pole. Whenever the DC gain and the high frequency gain are finite, you know you are going to have 1 0 1 pole. But depending upon the value of the high frequency and DC gain, you can also say whether the pole is going to come first or the 0 is going to come first. Okay, so if the high frequency gain is lower than the low frequency gain, then you have to go like this. So you are going to start from h of 0, which is your DC gain, and if it's lower than the high frequency gain, then you have to encounter pole first and 0 next. Okay, otherwise you have to encounter 0 first and pole next if your infinite frequency gain is high compared to low frequency gain. Okay, so this is just an intuitive way of drawing the transfer function. So but we can actually derive the poles and zeros as well. So I'll now to find the poles and zeros of this transfer function, the DC gain we know is half. Now the only thing remaining is poles and zeros. So to find the poles and zeros, this impedance has to go to 0 at any finite frequency. Okay, at that frequency this impedance should not go to 0. Okay, Z1 I am calling it should not be equal to 0. Now at omega equal to 0, this impedance goes to 0, but at omega equal to 0, this impedance also, the impedance Z1, which is the parallel LR network, also goes to 0. So therefore you can't apply that condition to find the 0. Okay, now the other possibility to find the 0 is when this impedance, that is the impedance between the input and the output, can blow up to infinity, and that will happen when SL equals minus R, or that's your 0 which is at minus R by L. Okay, now that's your location for 0, and at that frequency we can easily show that this impedance here doesn't blow up to infinity. Okay, again this will blow up to infinity at minus 2R by L, but that's not a condition for 0. Okay, but so at the frequency minus R by L, this impedance is finite. The impedance of this part is going to be finite. So the 0 can be found by using this, and the 0 is minus R by L. Now to find the pole, again you can short the input and find the equivalent inductance, which is going to be L by 2, and the equivalent resistance, which is going to be 2 by 3 R. Then the time constant is going to be effective inductance by effective resistance, which is L by 2 into 2 by 3 R, which will be 3 by 4 into L by R. Okay. Now your pole is going to be 4R, 4 by 3 R by L. Okay, your 0 is actually R by L and the pole is at 4 by 3 R by L. So here your 0 comes first and then the pole comes after that. Okay. Now finally I'll discuss the transfer functions which contain a 0 at 0. So far when we discuss the transfer functions, we just have to find the DC gain and poles and zeros. We could write the transfer function completely. But when you have a 0 at 0, we already discussed for RC circuits, we take a slightly different approach to write the whole overall transfer function. So we'll just take one circuit which has a 0 at 0. Okay. Now this circuit, if you see, to find the 0, I just need to equate this impedance to 0. That happens when S equal to 0. At that frequency, this impedance is finite. That's going to be R. So therefore I can apply that and there is a 0 at 0. Now next, to find the pole, I can simply find the short circuit the input and find the equivalent inductance seen by the resistance. So the time constant is going to be 2L by R, or the pole is going to be R by 2L. So we know the pole. We also know that there is going to be a 0 at 0. Okay. Again, the other 0 is when this impedance blows up to infinity. That happens only at omega equal to infinity. So I'll ignore that condition. So to write the transfer function, I'll just first write S by 1 plus S by omega p. That will be S into 2L by R. Now I'll first define a coefficient k, constant k here. Now we need to find what is the value of that constant. Now this value of k can be found either using the high frequency analysis, analyzing the circuit at high frequencies, or by analyzing the circuit at low frequencies. Either way we can find it out. So first I'll go for the high frequency approach, meaning I'll assume the frequency is very high, then this transfer function reduces to Sk by S 2L by R. So then we just have to find the value of k, which is actually, now we'll have to find the value of k. The transfer function we know reduces to this value for high frequencies, and this circuit at high frequencies, I can ignore the value of resistance in series with the inductor. It reduces to L and L. Okay. From this, the value of the high frequency gain is simply half. From the circuit we can find what is the value of the high frequency gain, and we equate it here and get the value of k to be half, get the value of k to be 1. So the transfer function, okay, k to be, actually it's not 1, it is L by R. Okay. So from that I can write the transfer function as SL by R by 1 plus S 2L by R. Now there is other way, which is the low frequency approach, wherein I am going to analyze the circuit at very low frequencies and try to predict the transfer function at low frequencies. Now at low frequencies, if you see this transfer function, which is Ks by 1 plus S by omega p, at very low frequencies, when I say low frequencies, frequencies close to DC, which will obviously be less than omega p. So the transfer function will reduce to simply Ks, right? This term will be proportional to j omega. So for low frequencies, I can ignore this term and it will be equal to simply 1. So you get the transfer function approximately Ks. So from that, I just have to derive the low frequency transfer function for this circuit and equate it to this, and we can get the value of k. So again, at low frequencies, when you have a series RC circuit, RL circuit, I can ignore the inductor because resistor impedance will dominate. The circuit simply reduces to this. Again, at low frequencies, I can assume the voltage across the inductor to be very, very small. So Vi is entirely going to drop across R. So the current through R is going to be Vi by R. That current, when I multiply by the impedance of the inductance, which is SL, I am going to get V0. So the transfer function at high frequencies is going to be, low frequencies is going to be SL by R. So if I equate Ks equals SL by R, I am going to get K as L by R. So we can obtain the value of k using the low frequency analysis approach or a high frequency approach. You will get the same value for both. Okay. So that's it about the analysis of first order RL circuits. So in this lecture we just mainly saw about how to analyze first order RL circuits and then derive transfer functions using intuitions. We already derived these transfer functions for RC circuits, first order RC circuits. Okay, it's very similar, in a similar way. I just wanted to show it for first order RL circuits. I'll stop at this point.